On behalf of the Aircraft Engine Historical Society, my name is Tom Fay, and today I'd like to talk about the dual rotation prop fans beyond the GE36 and the 578DX of the late 1980s. Specifically, the Lotarev D-236T of 1985, the Ivchenko-Progress D-27 of 1987, and the Safran Open Rotor of 2017. In a shameless plug for previous videos and for the economy of time, I can say that there is a wealth of background information on the design issues and technologies of the prop fan engines in the two previous videos published by the Aircraft Engine Historical Society. The titles and links for these videos are shown towards the bottom of this slide. These three previous prop fan engines will only get peripheral consideration in today's video presentation. Because of different governance ideologies, the long-running nature of some of the engine programs, the proprietary nature of these engine programs, and corporate gamesmanship, accurate and detailed technical information on these three engines has been challenging to unearth. I can cite where I found the information presented herein, but in most cases I cannot verify its absolute accuracy or accuracy to a point in time. Any errors are completely my own. There is a common technology used in the 578DX, D-236T, D-27, and Safran open rotor engines, that being the differential planetary gear reduction system used to reduce the 6,000 RPM of the power turbine down to about 1,000 RPM to drive the prop fan rotors. A sun gear resides in the center. Planet gears held in the planet gear carrier orbit the sun gear, and the planet gears mesh with the outer ring gear. For the dual rotation prop fan application, engine power is delivered via the sun gear in the middle to the planet gears, and both the planet gear carrier and the ring gear are free to rotate. The reduction ratio is determined by the diameters of the planetary gears. This video shows how the unrestrained triangular-shaped planet gear carrier and the unrestrained outer ring gear are driven in opposite directions, and this is how contra-rotation is achieved in the prop fan drive shafts. The sizing of the planetary gears determines not only the reduction ratio, but also how torque is divided between the two output shafts. This torque split is due to the different lever arm lengths between the gear centers. Some engines used a dual set of back-to-back planetary gear sets to achieve the desired reduction gear ratio. The use of a differential planetary reduction gear train provides a mechanism to have a different RPM on the two prop fan rotors, and this might be desirable for acoustic, vibratory, or efficiency purposes. Like the differential on a rear-wheel drive car of old, as one wheel, or prop fan rotor, slows down due to increased drag, the opposite rotor, or wheel, will have the tendency to speed up. An automobile has the ground to modulate drag, while propeller pitch is what modulates the drag on the individual prop fan rotors. This means that the blade pitch on the prop fan rotor discs must be independently controlled on each rotor disc. The two prop fan hubs, and thereby prop fan blades, are not mechanically linked in a clockwork lockstep. The hubs or blades can pass each other at variable clock positions. However, these passings can be held in a clockwork lockstep by the synchronizing and synchrophasing controls that adjust propeller pitch on the respective rotors. The incredible centrifugal, torsional, aerodynamic, and drive torque forces on these highly loaded blades require substantial power to change pitch, and this is typically accomplished by artful counterbalancing of the blades themselves and high-pressure hydraulic rams. The control systems to provide constant speed operation, anti-icing, synchronizing, synchrophasing, feathering, reversing, negative torque detection, and pitch locking to control a 16,000 horsepower turboshaft engine with both sensitivity and millisecond response times is both extremely complicated and fraught with peril. And now on to the oldest of the modern dual rotation prop fans, the Lotarev D-236T, which was a Russian contemporary of the American GE-36 and 578DX engines of the late 1980s. Technical details for the D-236T were scarce in the West during the middle to late 1980s. This article in the June 5, 1989 edition of Aviation Week and Space Technology provided welcome insight as well as photographs of the engine. Some people opined at the time that the D-236T was simply an advanced turboprop engine that had contra-rotating propellers. However, the multiple, thin, highly loaded composite blades meet some of the prop fan criteria. Plus, it was too cool for me to dismiss and neglect, so here is what is known. The size of the engine can be seen in these blown-up photographs from the AvWeek article. The Lotarev D-236T, known later as the Ivchenko-Progress D-36T, was a three-spool turboshaft engine designed by Vladimir Lotarev starting in 1979. It first ran 6 years later in 1985, and its first flight was in 1987. Like the Pratt & Whitney Allison 578DX, the power section for the D-36T was derived from a heavy-lift helicopter engine, in this case the D-136 turboshaft engine that passed testing in 1978 and went into production in 1982 for the Mi-26 helicopter. The three-spool D-236T prop fan engine first ran in 1985 and flew on a testbed aircraft in 1987. Only 5 Lotarev D-236T engines were produced. It was a three-spool engine where 2 of the spools were dedicated to the gas generator, and the third spool was the free turbine, which drove the reduction gearbox. A 7-stage high-pressure compressor was driven by a single-stage high-pressure turbine. A 6-stage low-pressure compressor was driven by a single-stage low-pressure turbine, and a 2-stage low-pressure free turbine drove the drive shaft, which went into the reduction gearbox. And the output of this shaft into the gearbox was about 6,200 RPM at takeoff. The overall pressure ratio of the engine was 18.3. The differential planetary gearbox had a 5.64 to 1 ratio with a 41% aft, 59% fore torque split. Horsepower was 9,400 equivalent shaft horsepower at takeoff and about 6,300 equivalent shaft horsepower in cruise. There were 8 fore prop fan blades and 6 aft prop fan blades. The prop fan RPM in cruise was about 960 RPM with a reported 87% propeller efficiency. Prop fan RPM at takeoff was 1100 RPM. This photograph shows the D-236T installed on an Ilyushin IL-76 testbed. It used Stupino SV-36 propellers, which were 13 feet 9.5 inches in diameter. The blades were constructed from fiberglass and carbon fiber with an I-beam metal spar that extended out to half span. De-icing wires were embedded in the propeller blade matrix. Of note is that the propeller blades were not scimitar-shaped, and except for the tips, which were swept, they are relatively constant chord through most of their span. A normally 4 turbojet Ilyushin IL-76 was modified to accept the D-236T in the number 2 position on the port wing pylon. Some 36 flights produced 70 hours of in-flight testing of the D-36T. The D-236T was eventually installed on the starboard pylon of a normally tri-jet-powered Yak-42, becoming the Yak-42LL. This aircraft was displayed and flown for the first time in the West at the International Air Show held in August of 1990 in Hanover, Germany. The Yak-42LL was also displayed at Le Bourget in 1991. Unlike the American Propfan blades of that era, note that the Stupino propeller blades are very nearly constant chord, with only the tips being swept. The design maximum cruise speed for the Yak-42LL was 0.7 Mach at 36,000 feet, or roughly 462 miles per hour. A cruise-specific fuel consumption of 0.359 was impressive, and they did experimental work with differential rotor speeds. However, no specific performance data has been unearthed. The D-236T was initially intended to power the Antonov An-70 medium transport aircraft, which started development in 1981. Ultimately, the D-236T proved underpowered for the forthcoming 4-engine, high-wing Antonov An-70, and this engine faded from the propulsion scene. The big dog on the Propfan block is the Ivchenko-Progress D-27 engine, designed by Fedor Muravchenko of the Ivchenko-Progress Zaporizhia Machine Building Design Bureau. Unlike the West, Soviet industrial philosophy separated the design function from the construction function of these engines. The engine was manufactured by Motor Sich in Zaporizhia, Ukraine, and can produce up to 16,000 horsepower. Design work started in 1985, and the engine first flew an aircraft, the An-70, on December 16, 1994. The D-27 is a 3-spool engine, meaning 3 different shafts are used in the design. The gas generator section uses 2 spools, where the low-pressure spool and high-pressure spools are each driven by their own low-pressure and high-pressure turbines. The Propfan gearbox is driven by the 3rd spool that carries a large diameter 4-stage low-pressure turbine. In detail, starting at the front from the left, is the 2-stage planetary differential reduction gearbox. This is followed by a 5-stage low-pressure compressor with variable inlet guide vanes and 2 variable geometry stator rows. The low-pressure section is followed by the 2-stage axial and a single centrifugal high-pressure compressor section. Further down the line is the single stage for the high-pressure turbine, which drives the high-pressure compressor, followed by a single-stage intermediate pressure turbine for the low-pressure compressor, and lastly, the 4-stage low-pressure turbine that drives the prop fans. Overall pressure ratio is about 29, The engine itself, no propellers, weighs about 3,600 pounds. Cruise-specific fuel consumption is about 0.31, which is excellent, and it makes about 25,000 pounds of static thrust. An overall pressure ratio of 29 is in the range of the CFM56 turbofan engine, which has a pressure ratio anywhere from 25 to 38 that went into service in 1982. The cruise-specific SFC of 0.31 is exceptional, as the CFM56 turbofan varied from 0.5 to 0.67. The much lower power Allison T56 engine has a cruise-specific SFC as low as 0.4, and the 12,000 horsepower Kuznetsov NK12 has a cruise SFC of about 0.36. One interesting engineering challenge is how to attach the 2,400-pound propeller set to the engine. You can see the serrated flange, sometimes called a hearth coupling, on the nose of the D-27. The dual rotor Propfan set is attached to this hearth coupling with 24 bolts, and this coupling accepts all of the loads: thrust, centrifugal, precessional, asymmetric, aerodynamic, vibration, etc., of both propellers. There is a center shaft that transmits torque to the 4 propeller set, but only drive torque. It does not take any other loads except for torque. This dual rotation propeller system was pioneered by the Stupino Design Bureau for Special Machine Building and used on the Kuznetsov NK12 engine starting in the 1950s, as used on the Tu-114, Tu-95, and AN-22 aircraft. I assume the same architecture is used on the D-27 Propfan. The hearth coupling is shown in blue highlighter, while the torque shaft for the contra-rotating 4-propeller unit is shown in yellow. The aft end of the propeller set that bolts to the serrated hearth coupling is shown lower left. This drawing shows the details of the AV contra-rotating propeller assembly. The coupling is shown in aqua blue at the right that drives the red aft propeller hub. The torque shaft for the 4 propeller is inserted into the center bore of this assembly to drive the 4 propeller assembly, which is shown in pink. The front propeller is secured into the aft section by the heroic ball bearing shown in the center of the drawing and a smaller bearing in the aft part of the pink section, which allows the 4 hub to spin inside the aft hub, but with the aft hub taking all of the propeller loads. The center of the yellow torque shaft carries oil tubes to control the pitch mechanism of the 4 hub, while the oil lines for pitch control of the aft hub come through ports in the hearth coupling. This stout design eliminates the large, long, very overhung, whirling prop shafts of earlier and lower-powered engines, where each of the concentric contra-rotating shafts had to take the propeller loads of their respective prop discs. Getting back to the D-27 Propfan, the D-27 uses propellers designed by the Aerosila Special Design Bureau, formerly Stupino. The Propfan set weighs 2,400 pounds and handles up to 16,000 horsepower, while the propulsion system weighs around 6,000 pounds. This photograph shows the D-27 development engine in the number 2 position on the Ilyushin 76 LL testbed aircraft. The first flight demonstration in the West of the D-27 occurred in May of 1994 at the Berlin Air Show. Note that even these prototype Propfan blades on the D-27 are now more scimitar-shaped than the constant chord blades used on the D-236T. This close-up of the D-27 on the Ilyushin shows a propeller sensor data cable running from the spinner to the fuselage, and it is assumed that this cable acquired information on either blade stress or vibration. This photograph shows the starboard wing of the An-70 aircraft with the Stupino SV-27 propellers. There are 8 blades on the fore-rotor and 6 blades on the aft rotor, and this design could be to either vibration or noise reduction, perhaps efficiency, or due to the torque split of the reduction gearbox. They are composite blades, and they rotate anywhere from 850 RPM in cruise to 1,000 RPM at takeoff, and the fan diameter is 14 feet 9 inches. The cruise speed of the An-70 with the D-27 engines has been stated to be 465 miles an hour, and the maximum payload approaches 52 tons. The An-70 has had a long and tumultuous career. Its first flight occurred in December of 1994, but a couple months later it was lost on its 4th flight due to a mid-air collision. An existing static test airframe was converted to flight prototype number 2 and first flew in 1997. This aircraft lost control of the aft propeller on the number 3 engine with a series of failures that caused a forced landing immediately after takeoff in January of 2001. The aircraft was repaired and reflown 5 months later. In July of 2010, there was a significant update of systems, engines, and propellers, and it was reflown in September of 2012. These photographs show the Antonov An-70 in the 1998 time frame, while the photograph at the bottom shows the modernized An-70 around 2012. Note that the prop disc spacing was increased from 24 inches to 35 inches for noise reduction. This is an interesting graphic published by Antonov comparing the modernized An-70 to the Airbus A400M Atlas military transport that first flew in December of 2009. The Antonov is in light blue-green camouflage and is overlaid on a scale image of the gray A400, showing the similar sizing. Here is the data table that accompanied the previous graphic, published in perhaps 2013, contrasting the An-70 and the A400M. Of note is the acquisition cost and load carrying capacities of the two aircraft, which are otherwise, and for the most part, highly comparable in performance. Here, in a trail of tears, is the status of the An-70 as the sole user of the D-27 Propfan engine. The Progress Design Bureau is a design organization founded in 1945, established in Ukraine 1990, and administered by the Ukrainian defense industry, and is tasked with the designing of aircraft engines and systems. This facility was attacked by Russia and severely damaged in 2022. Motor Sich is located in Zaporizhia, Ukraine, and is the production organization that builds components as well as engines for aircraft and industry. Motor Sich severed ties with Russia in 2014. China acquired 41% of the company in 2017, and the Ukraine government seized and nationalized Motor Sich in 2022. This facility has been attacked by Russia starting in May of 2022 through January of 2025. The Antonov Company is an aircraft manufacturer and services company founded in 1946, based initially in Russia of the RSFSR. Antonov moved to Kyiv, Ukraine in 1952. This was attacked by Russia and severely damaged in February of 2022. Aerosila is a Russian company based in Stupino, Russia, outside Moscow, that builds and designs propellers, gearboxes, governors, pumps, hydromechanical actuators, and APUs. The D-27 engines and Antonov airframes were designed and built in Ukraine, while the propellers are designed and built in Russia. Political loggerheads and now war has made the An-70 untenable for use anywhere in the world. The latest and most modern Propfan in our discussion today is the Safran Open Rotor, relabeled by Safran as the Contra-Rotating Open Rotor, or CROR, to differentiate this engine from the latest single-rotation Propfan engine, which we'll mention briefly later. This was a European-funded initiative that started in 2008 with an engine running on the test stand in May of 2017. The gas generator, which spins the third-stage free turbine to drive the reduction gearbox and ultimately the Propfan rotors, is based on the Snecma M88 turbojet, which is used in pairs in the French Rafale fighter. The M88 is a low-bypass, two-spool turbojet engine with a three-stage low-pressure compressor, a six-stage high-pressure compressor with variable geometry stator blades. Each compressor spool is driven by its own single-stage turbine, and the overall pressure ratio is 27. This is the general layout of the Safran CROR. The gas generator has a low-pressure spool, shown in dark blue, and a high-pressure spool, shown in red, whose purpose is to generate and deliver a large volume of fast-moving exhaust gas into the multiple-stage, low-pressure free turbine that drives the gearbox. The three-stage low-pressure free turbine, shown in purple, drives the input, or sun gear, into the differential planetary gearbox shown just downstream of the purple turbine. The planet gear carrier drives the aft power frame, shown in red, and the ring gear drives the fore power frame, shown in blue. A more detailed look at the Safran CROR shows a three-stage low-pressure compressor being driven by a single-stage low-pressure turbine, a five-stage high-pressure compressor driven by a two-stage high-pressure turbine, and furthest downstream is a three-stage free low-pressure turbine which drives the Propfan gearbox. The bypass ratio for the system exceeds 30-to-1, meaning 30 times more air is flowed through the Propfan blades than through the engine. The diameter of the nacelle is dictated by the diameter of the gearbox, the internal exhaust stream tunnels, and the structure required to secure the blades to the power frames. Based on the GE36 Propfan experience, a considerable volume of air is required to cool the rotating components and assure that the Propfan blade bases do not exceed approximately 275 degrees Fahrenheit. The exhaust flow, shown in red here, impinges upon the structure of the rotating power frames, and thus active cooling is likely required. Looking closely at the Safran CR-OR on the test stand, small yellow scoops angled to the local airflow and pressure can be seen on both of the rotating power frame nacelles. These are likely cooling air intakes for modulating the temperature of internal nacelle components, and this design was pioneered by Safran partner General Electric on their GE36 in the 1980s. The diameter of the scoop intake hole on the GE36 was 1/2 inch. According to a Safran executive, the CR-OR 4-rotor had a diameter of 13 feet 1 inch, while the aft rotor was quoted as 12 foot 6 inches in diameter, so a difference between the blade ends of 3.5 inches. Based on several side view drawings and photographs of the CR-OR on the test stand, the aft rotor diameter appears to me to be significantly smaller than the 4-rotor. Analyzing the Safran side view drawings, the aft rotor may be as much as 22 inches shorter in diameter, or up to 11 inches difference in the tip ends. Cropping the aft rotor diameter reduces the noise and vibration caused by the blade tip vortices of the 4-rotor impacting onto the aft rotor. Based on this screenshot from a Safran video clip, another use of GE36 technology is the use of a slotted base design to seat the Propfan blades. The blade receptacles for the GE36 as well as the Safran CR-OR are, by necessity, atypically shallow because deeper sockets would detrimentally enlarge the nacelle diameter. This slotted design provides sufficient strength for the highly loaded blades while allowing an individual blade to be changed with the engine or the rotor still on the aircraft. It is this view that indicates to me that the aft rotor on the CR-OR is more than 7 inches smaller in diameter than the 4-rotor. Based on Safran side view drawings, I estimate the distance between the rotor centers to be approximately 45 inches. Research has shown that, within limits, a greater distance between the rotor discs can reduce noise. The Safran CR-OR engine was run for 70 hours on the test stand, which included some time in reverse thrust. Safran and Associates spent considerable time and money on blade shaping to reduce noise while maintaining the efficiency of the Propfan design. The group made considerable progress on this challenge, and the shaping is unlike any blades seen heretofore. The details of their geometry, thickness, twist, area, loading, activity factor, etc. remain proprietary, but Safran has stated that the noise levels of the CR-OR are comparable with the LEAP turbofan engine-powered B-737 MAX and A320neo aircraft.
Stage 2 objective is to validate, by means of a ground test demo, a revolutionary engine architecture, the open rotor.
This project is an uninterrupted sequence of challenges, every phase of it. We had to put in place our best technical skills, advanced design tools, and advanced manufacturing techniques like additive manufacturing in order to solve the complex equation of this project.
And it's when you see the engine installed in the test bench and you perform the first run that you can realize and be proud of what the whole team have done these years.
Testing means refining all the components, not as standing-alone parts, but all together, like a music band, where every instrument has a fundamental role.
And we succeeded all together.
This was the public status of the Safran CR-OR in 2018, roughly a year after the engine was run on the test stand. Flight test target of the open rotor was in 2024-2025, development in 2030, entry into service in 2035. This incomplete timeline of the Safran CR-OR program begins with funding, design, and development in 2008-2009 time period. Assembly of the demonstrator engine began in 2015, and in May of 2017, ground running of the engine began. In September of 2017, flight testing of the engine on an A340 had been shelved due to airframe strengthening and weight concerns. Later, in August of 2018, Safran says that the first flight of the CR-OR is possible in the 2024-2025 timeframe. In December of 2018, the CR-OR, which had been run, was disassembled and sent to General Electric for analysis. And in 2019, Safran receives the Laureate Award from Aviation Week for the CR-OR engine. However, in June of 2021, Safran and GE announced that they had pivoted to a single rotation Propfan design with recuperation of exhaust heat and a set of variable incident non-rotating swirl recovery vanes located behind the Propfan rotor. This effectively replaced the CR-OR. The construction and testing of both subscale and full-scale RISE engine components is currently ongoing. Regardless of single rotation or dual rotation, Propfan engines present significant challenges for use on commercial airliners, which are typically low-wing aircraft. In this graphic is the laundry list of the major challenges, and the industry consensus is that a new airframe specifically designed for the Propfan engines will be required. Here is a summary data table for the 5 dual-rotation Propfan engines detailed in this AEHS video series. I will note that the figures in red are values derived from side view drawings as well as back calculation from published data by the author for this presentation, so any errors or misrepresentation are entirely my own. Of interest is the annular disk loading, which is the amount of horsepower absorbed by each square foot of annular swept blade area. The GE36 leads the group at 77 horsepower per square foot, while the D-36T is roughly half the loading of the GE36. It is debatable whether the Airbus A400M Atlas is a Propfan or not, but I can say that its annular disk loading is around 48 horsepower per square foot. The wild card in this analysis is the thinness, size, shaping, and RPM of the blades, which govern their efficiency and noise characteristics. The surface area and geometry of these prop fan blades is not available, so analyses of actual prop blade loadings cannot be made. However, an average thrust per blade is easily calculated, and the average thrust per blade value for the D-27 is almost double that of the Safran CR-OR. This would indicate that the modern approach prefers more blades at a lower power thrust loading to mitigate noise and perhaps reduce the effects of a blade-off condition. While data for the CR-OR is lacking, the GE36 still has the lowest reported specific fuel consumption of all the prop fans, but is perhaps also the heaviest at 2,500 pounds heavier than a LEAP turbofan on the A320neo, and it is also the fattest. Prop fan performance is 3D chess played with a few dozen design parameters, and that is before you get to cost, risk, regulatory compliance, and airline public acceptance. But make no mistake, prop fan technology clearly enabled the high bypass turbofans flying today. 8 years ago, this was the speculation on the CR-OR aircraft of the future. But today, these designs are the more likely to succeed. On behalf of the Aircraft Engine Historical Society, I thank you for your attention.